All right, let's get going here. Before I continue, a couple questions that came up after class. Let's look at the fundamental thing we're computing here. So a couple of people asked me, what happens, what is this class P, right? Maybe we're doing this over the set of all Lipschitz regression functions or whatever, so maybe it's a parametric family of distributions. Can you take this to be all distributions? Well, it depends on the problem. So in some cases, the answer is yes. If this is the CDF, and this is an estimate of the CDF, and if this is the maximum difference between the CDFs, then you could take this to be all distributions, and you get a rate, you get a minimax rate like this, and it's achieved by the empirical distribution function. But that's a pretty special case. When you're dealing with regression functions or density functions or classifiers, generally speaking, if you take this to be a set of all distributions, you're just going to get a big number here. It won't even go to 0. And so you can't do minimax estimation in that case. But the reason why we're taking a particular class P anyway, it isn't really so much that we're trying to necessarily solve it for a particular P. This is a way of getting an understanding of how difficult the problem is for a particular class P. So that the question you're really asking is, if I'm doing regression or whatever, and I restrict myself to the class of functions that are with twice differentiable functions, how difficult is that problem? So to answer that question, that's where this P is coming from. It's kind of part of the question. When we talk about active learning, you'll see that this will include, for example, something called the Sibikov noise condition. How sharp is the decision boundary? We'll come into it. And so you want to ask the question, if the decision boundary has this much sharpness, how hard is the problem? So it's sort of like you're asking the question, how hard is the problem when I use a particular P? That's where the script P comes from. Now, we're taking the info over all estimators because that's going to tell us then how hard it is to estimate that problem. Does there exist any estimator at all which gets a certain rate of convergence? But somebody did ask me, is it possible to restrict this? What if I want to restrict myself to certain estimators instead of the set of all estimators? So this is actually a very difficult question. It's not known how to do that in general. There's special cases where we know how to do it, but in general, it's not known. But it is an area of active research. So for example, it turns out sometimes the theta hat is just some complicated function of the data. And from a statistician's point of view, you're done. But then the computer scientists will say, but can you compute that in polynomial time? So you might want to restrict this to the set of all things that be computed in polynomial time, and nobody knows how to compute that then. Then there's been these papers about the differences between, there are some hints now in certain problems, like in sparse principal component analysis, where there seems to be a gap between taking the info over all estimators, which is mathematically what we do, and then if you did a restricted thing, it seems like there's a gap there, but it's not completely well understood yet. Another example of this is some work that John Ducci has done, where nowadays people are very interested in privacy, and there's this thing called differential privacy, which is a kind of a restriction on the kind of estimator you can use that ensures that you provide an informative answer, but you don't give away information about who's in the database. So you might want to restrict this to things that satisfy differential privacy. And so he has some results about how that affects the minimax rate and so on. But the general question of if I restrict myself to certain types of estimators, how to compute this, in general, it's not an easy question. So the way we're doing it in class today is somebody hands us script P and says, how hard is this problem? And we're going to take the info for all possible estimators. Okay, and that's what the proofs are all going to be based on that idea.
I think worth pointing out there's one more thing we've already seen, which is for non-parametric regression, we learned that if we take the info over just linear functions of y, it's just some linear function of y. We already saw that rate is very different than the info over all estimates if the class script P is big enough.
Right, if this includes inhomogeneous functions, regression functions, then we know that the minimax rate is achieved over an estimator which is a nonlinear estimator. So if you restrict yourself to linear smoothers, you won't get the minimax rate, for example. Okay, but we did Lecombe's lemma, which, let me just remind you what that was, because we're going to apply it now in the regression problem, which boiled down to the following thing, which was to apply it, you just pick two arbitrary distributions that are close in Kullback-Leibler distance. So let's say let's just get rid of constants here. They're about 1 over n away. And then the minimax bound we got was it's bigger than or equal to delta over 16, where delta is the difference between theta for 0 and theta for 1. So the problem we were starting to apply this to was we have regression data. We have the usual regression data. This is x random, by the way. And for simplicity, we're taking xi to be uniform 0, 1. And we took yi to be some unknown regression function plus epsilon. And for simplicity, we're making a lot of extra assumptions, like we're going to take the epsilons to be normal. So in other words, the joint density, p of xy, I could write as p of x times p of y given x. This is just equal to 1. And this is normal. So this is actually normal with mean m of x variance 1. And the function class m was the set of all functions that are Lipschitz. We're just doing the one-dimensional case. So all I have to do is pick two distributions and see if I can get it to work out. It's kind of I have to just guess and see what we get here. And to make things even simpler, I said we're going to take the loss function, and instead of being L2 loss, we're just going to compare it m hat. So the d is going to be m hat at a particular point x0. I picked 1. I picked 0, rather. But there's nothing special about 0. Pick any point in the sample space. We'll get the same answer. OK, is the setup clear? So now I'm going to show you how do I pick two distributions. Well, picking two distributions amounts to picking two different regression functions. And here's the intuition. You want to pick them as close together as possible in the sense of, or I should say, you want to make them as far apart as possible in the sense of making this, their values, where's the d? This thing as big as possible, but close together statistically. So I'm going to show you what the answer is. We're going to take m0. So we're going to pick two functions now, m0 and m1. Once I pick the two regression functions, that specifies the whole distribution. The first one I'm just going to take to be the 0 function. That satisfies the Lipschitz condition. It's just constant. And the second one I'm going to take to be this one. So by making it equal everywhere, I'm trying to make them as hard to distinguish as possible. But I want to make sure that they do differ at 0, since I'm measuring them at 0. If I was doing this somewhere else, by the way, suppose I had picked x here, then I would pick 0, and I would pick a function that looks like this. Okay? And this length is, say, epsilon, and this height will be L epsilon. I picked that. The epsilon is a tuning parameter we're going to pick. And the reason why I pick L epsilon is now you can check that it satisfies the Lipschitz condition. Those are the two functions, m0 and m1. If we had done smoother functions, suppose instead of having Lipschitz, I had wanted things with twice differentiable or something like that, it's still going to be, the construction's always the same. You're going to pick one of them typically to be the 0 function and one of them to have a little blip. You just have to make sure it's smoother now. So those are typically the two guys you're comparing. You want to make that the values of the thing you're estimating, here it's the function value here and here, you want to pull them apart, but otherwise make them as close as possible together so you can get the Kullback-Leibler distance close together. So the actual formula here, which is, we're on page 5 here of the notes, is that m1 of x, you can see that is L for 0 less than x less than epsilon, and 0 otherwise. So now, to compute the KL distance between these two implied distributions, well, that's pretty easy because let's call the distribution, there's two distributions we've defined now, right? P0 and P1, but they both have the same marginal. They both have a uniform on x. So all that differs is the conditional distribution. And these are, in fact, the same, except that this is normal 0, and this is normal m1 of x. Okay? And the joint Kullback-Leibler distance, which would involve integrating over x and y, we can break it up into integrating over x and integrating over y. And because I've made the marginals the same, it just simplifies to basically computing. What I'm really doing is, you can think of there as being a normal distribution above the board here and a normal distribution above the board here. And there's over every slice, there's a normal, because this is the y direction. And this is x. And you can see what's going to happen is I'm just taking, what it really amounts to is I'm taking the Kullback-Leibler distance between these normals at every slice and then integrating that. The distance is 0. These are identical here. So all I need is the Kullback-Leibler distance between a normal centered here and a normal centered here, integrated over x. I mean, the calculation is done exactly for you, but I'm just telling you intuitively what's going on. Does anybody remember what is the Kullback-Leibler distance between two normals with variance 1? Anybody remember that? If I have a normal with mean theta 1, normal with mean theta 2, has anybody ever computed the KL distance? Okay. Right. It just turns out to be the square difference. So the KL distance here just ends up being the integral from 0 up to epsilon, because it's 0 after that. And then it's this distance. Well, in other words, this minus this squared. That's it, which is this. So it's, let's see, it's L squared over 2 epsilon minus x squared dx. Okay, and the full calculation is right there, but it's just breaking it up into y given x and x. And when you do that integral, you get L squared epsilon cubed over 6. Now notice I had this kind of free parameter epsilon, which was where to make the breakpoint. But that's determined because remember the goal in applying Lecombe's lemma is to make this to be about 1 over n. So we're going to set this equal to 1 over n. Let's say set this to be 1 over n. There's really a constant there, log 2 over n. And solve for epsilon. And what you get is that epsilon is some constant over n to the 1/3. So now, now we apply Lecombe's lemma, or really that corollary, which said that once I find two distributions that are 1 over n apart in Kullback-Leibler distance, the minimax risk is given by delta over 16, delta being how different those functions are. And how different are they? Well, they're L times epsilon apart. So we've got the risk the risk, the lower bound, this is all about lower bounds, remember, is L times epsilon. So an epsilon we said is basically n to the 1/3. Again, I'm going to throw away constants. We've done it. We now have a lower bound. Okay, so it is a lower bound, but we don't know if it's a sharp lower bound. Okay, I just kind of arbitrarily picked two things that had a Kullback-Leibler distance 1/n and said how far apart they are. That's my bound. By the way, for some reason I worked on the absolute scale. We usually work on the squared scale. So if I just did squared here, of course this would be 2/3. But I'll stick to the notes and do it on the absolute scale. So what I know is a lower bound. To get an upper bound, I have to pick a particular estimator, but we've done estimators for regression. So in particular, for the Lipschitz class, I don't know if we did the, you can think of this as a 0th order spline, I guess, but I'm thinking of what's sometimes called the regressigram, where you just, it's like a histogram, but it's for regression. You just chop up this axis into pieces and take the average over each piece. Is that a 0th order spline? Not quite. Okay. Sort of like a spline. I mean, a piecewise linear, a piecewise constant function will do it, because we're only assuming it's Lipschitz smooth. So if we do this and just do the same analysis we did earlier in the course, just compute the bias and the variance, you'll get n to the 1/3. It's analysis that we've done before. So we also have an upper bound of 1/n to the 1/3. And what we've just proved is that the minimax risk for estimating a regression function at a point is n to the 1/3, because we have a lower bound, upper bound, and they match, at least up to rates. We could have kept track of the constants, and they wouldn't have been that different, actually, but just worry here about the rate.
Sorry, that actually is exactly a 0th order.
Okay, so this is a 0th order spline.
If you just plug in k equals 0 in any of the formulas, that's the rate there.
Yeah. Okay, so we've already derived that one. So the way we would write this now is what we've proved is that the inf over all possible estimators and the sup over all p in this class that we're dealing with and I'm going to write it again in the statistical notation. That's an upper and a lower bound, n to the 1/3. I did this in one dimension to keep it simple. A good exercise, if you want, is do this in d dimensions. It's just a bit messier, but it's the same construction. What you would do, instead of dividing, think of the axis now, instead of taking a little thing here, you could put like a little pyramid kind of thing over as a blip there. And what's going to happen in the d-dimensional case is you're going to get 1/n to the 1/d plus 2. Or if we'd done it on the squared scale, as we normally do, everything would just be squared. So actually, that will look more familiar to you. If we did it on the squared scale, you're going to get the minimax rate is 2/d plus 2. If you now added more smoothness, conceptually it's not that hard. It's just the calculations are a little bit messier, but it's actually very simple. You just take a blip which is smoother. You just make a little bump which is twice differentiable, or in general beta times differentiable. And what you're going to end up with is just this. Okay? So the calculations are a little bit different, but conceptually exactly the same thing's going on. Okay, any questions? That's a good example because it really is very, very typical of the kind of construction one tries to do. But let's suppose we wanted to actually bound not the loss at a particular point, but something we're more familiar with, which is something like this. Suppose this was our distance. It turns out that actually, before we do that, let's do another example. I just thought of Before I came in here, I put down a note to remind myself. It's not in the notes, but yeah, here it is. That we should revisit something really simple using Lecombe's lemma, which is, let's go back to the simplest parametric case we ever did. We did this in 705 using a Bayesian argument to get a minimax rate, but here's how you would do it using Lecombe's lemma. Suppose, let's just go back to the normal distribution. X1 to Xn are from a normal, theta 1. Do you remember when we found the minimax rate in 705? Does anybody still remember that? We did a fairly elaborate argument to get that x bar was minimax, but we can do a similar thing, although it's less precise here, using Lecombe's lemma, and it's very simple. All I'm going to do is pick two distributions in here. So how about I pick theta equals to 0 and theta equals to, so let's call that theta naught, and theta equals to something else. What do I know? Well, I want to apply Lecombe's lemma. I want to pick two things whose KL distance is about 1 over n apart. Again, the Kolbeck-Leibler distance between, so I'm doing 0 and then this point. But the KL distance is theta squared over 2. We just said that. I want that to be 1 over n. So what does that tell you? It tells you theta has to be about 1 over root n. Right? We're done. That's how easy it is, right? Because what's Lecombe's lemma says, once I find two things that are 1 over n apart, the lower bound is now delta over 16. Delta is the difference between these, which is, so this is about, I'm ignoring some constants here. So and that's on the absolute scale. Again, if you wanted it on squared scale, if we took d to be theta hat minus theta squared, it would be a lower bound of 1 over n, which matches x bar, right? X bar, what rate does x bar go to 0 at in mean squared error? 1 over n. The difference between this argument and the one we did in 705, one in 705 gave us the constants exactly. This is just giving us the rate. There's some, if you actually put in the constants here, you get like 1 over, there's a 16, well, there's a 16. It's not going to be tight. So Lecombe's lemma is used more for non-parametric cases where we're less concerned about constants and more concerned about rates. The argument we did in 705 is a little bit more precise, but it's restricted to parametric families. Okay. Let's move on, though, to how do I do something like an L2 difference. And it turns out that Lecombe's lemma isn't quite tight enough. It'll actually get you pretty close, but people prefer to do a more precise argument. And what we do is we replace the Neyman-Pearson lemma, which was at the heart of how we proved Lecombe's lemma, with something called Fano's inequality. But before I do that, let me show you the kind of construction we're going to use so you see why we need to do that. So if I take this, and you can see that the alternative distribution we constructed was a blip, something like this, let's say, right? That's not going to give us a sharp enough rate because it's not taking into account that we're adding up the error over the whole function. So what you do is instead of considering a two-point hypothesis testing problem, you consider like a multiple hypothesis testing problem where I consider many different functions, a blip here, maybe a blip here, maybe a blip here, like this. So I'm going to consider a base function plus many different blips. There's going to be many possible functions. Intuitively, that's going to allow me to take into account that we're trying to estimate the whole function. So all that happens is that we should now think about testing not one hypothesis, not testing, in other words, between two possible distributions, but trying to choose between many distributions. And this is Fano's method. So remember that we reduced the proof of Lecombe's lemma to really this 0, 1 function, which was picking Did the data come from P0 or P1? Now we're going to consider finitely many. So what's going to happen is this. So this is, first I'm going to state Fano's lemma, which is, there's Fano's method and Fano's lemma. Fano's method makes use of Fano's lemma. Fano's lemma is just a basic lemma from information theory. And it says the following. Suppose I have n observations drawn from some distribution P. And all I know about P is it's in some finite set. P1, P2, up to Pn. Okay, so I give you some data points, and I tell you it's from one of, they're all from one of those distributions. They're all drawn IID from one of those distributions. Your job is to guess, produce a guess, let's call it z. So z is some function of the data. So z is any function of the data, and z is going to be an integer. It's going to be 1, 2, up to n. In other words, you're going to take the data, you're going to do whatever you want with it, and then you're going to say, okay, it came from this distribution, or no, it came from this distribution. You're trying to guess which distribution generated the data. So that's what your z is. And what Fano's lemma says is the average error the probability when I generate the data from the jth distribution that z is not equal to j. So this is, I generated it from j and you got it wrong. The average of those errors, so that's an error, right? So the average of that over all distributions is bigger than or equal to 1 minus n beta log n, where beta is the maximum over all pairs here of the Kullback-Leibler distance between those. It's a kind of an odd-looking expression, but you'll see the idea is we're going to make this, we're going to eventually choose beta to make this like smaller than this, which will give us our minimax lower bound. So I haven't yet shown you how to get the minimax lower bound, but we're going to get there pretty quickly. Now, how do you prove this? I actually put the proof in the appendix. It's a few pages long, so I didn't want to go through it. It's just some elementary facts about Kullback-Leibler distance, basically. Okay, it's a standard result from information theory. If you want to see the proof, though, it is, I'm pretty sure, yeah, it's lemma 30 in the appendix of the notes, okay? Think of it, though, as just a generalization of the two-point thing we did, kind of a name, that name in Pearson's kind of thing. This is kind of an endpoint version of that. Okay, so now we can immediately get a lower bound as follows. So I want to get a minimax lower bound over some class of distributions. The first thing I'm going to do is I'm going to say, just like we did before, we restricted ourselves to 2-point sets to get a first lower bound. Well, now I'm just going to restrict myself to some n-point set. So this will be now P in some class P1 to Pn of the same thing. So now I've restricted it to this finite set. And here we go. The theorem, this is theorem 10, says that this, now that I've restricted it to a finite set, that's bounded below by the following quantity. So remember in Lecombe's lemma, we kind of had how far apart the S-demands were, and then something like that integral of the densities or the KL distance, right? Same here. We're going to have this alpha over 2, and then we're going to have this thing from Fano's inequality. Where beta I've already defined. What's alpha? Alpha is the distance between the closest of these. Over j naught equal to k. So picture it this way. I'm choosing a finite set of distributions. Once I've chosen them, there's only two things I have to compute. I take the KL distance between any pair and take the max. That's beta. Then I take the quantity of interest, which is maybe the L2 distance. Say that's a regression function, that's a regression function, and say we're interested in the L2 distance. And I take all possible pairs and I take the minimum. Okay? And that's what the Fano inequality is. And in particular, just like we did for Lecombe's lemma, I took a particular choice to get out a concrete answer. We're going to do the same thing here, that as long as I'm going to now give you a recipe. The way you want to pick these is to make beta, again, small enough. So suppose, this is corollary 11, suppose you choose beta, you choose these distributions so that each pair has a KL distance. So in other words, beta is less than or equal to log of the number of things in there over 4 over n. Then what I've done is make sure, what I've done now is this is bigger than or equal to a quarter. That choice makes this bigger than or equal to a quarter. So if I choose beta that way, it implies my minimax bound is bigger than alpha over 4. There's the answer. So let me repeat that. You take, what we're going to do is take the set of all distributions. We're going to somehow carefully pick capital N distributions. We have to decide what capital N is going to be. We're going to space them out to try to make them as far as possible in this sense, that the functions are all slightly different. But when we compute the KL distance between any pair, we have to make sure they're less than this. And then it follows immediately from that lemma that there's your minimax lower bound. Any questions before we prove it? Okay, the proof is actually quite short. It's really the same proof we did with 2 points. The only thing is, instead of the Neyman Pearson step, we plug in Fano's inequality. So here's the proof. Remember, though, you're giving me an arbitrary estimator. I've picked out for my proof some finite set of distributions. You give me any estimator, and just as before, that defines a kind of selection of these, namely the closest one. All right, so you give me any theta hat, and I'm going to define z to be equal to the closest, the theta hat, well, it's argmin over all j. Right? So if your estimator was here, then I'm going to guess this guy. So again, your estimator defines a selector. Okay. And it's easy to see again by the triangle inequality, like we did before, that the expected distance under, say, the jth one of the distance between your estimator and theta of pj is at least half the distance between any of these times the probability you pick the wrong guy. If you pick the wrong guy, you've got to be at least alpha away. So this is, or at least alpha over 2 away. So this is bigger than or equal to alpha over 2 times the probability of picking the wrong guy. Let me make sure that was clear. So let's suppose this is the truth, and I'm trying to say how far are you away. But if your guy is over here and you select the wrong guy, then we know, since these are spaced apart at least alpha, that the error you've made is at least alpha over 2 times the probability you picked the wrong guy. That's a lower bound. You picked the wrong guy, and they're spaced apart by alpha, therefore you've made at least this much error. And that's true for each j. So if I just take the maximum, therefore, I get that the maximum over all j of that thing is bigger than or equal to alpha over 2 times the maximum selection error. Now we can do the same trick we did before for Lecombe's lemma, which is the maximum is always bigger than or equal to the average. So this is bigger than or equal to alpha over 2 times the average error. And now we just plug in the Fano inequality. And we're done. So that's so in a sense, we've reduced the Minimax problem to a kind of like a multiple hypothesis testing problem, is the way to think about it. Let's see how we're doing. Any questions? Everybody's very quiet. Kevin.
So this is a general framework. So what could go wrong such that deriving the minimax is no longer so straightforward?
Oh, wow. In many cases, it's fairly easy. Just before I came into this room, I was meeting with a bunch of our friends from ML, some students in ML, who are desperately trying to compute the minimax lower bound on a particular problem, and they've been struggling over it for weeks. It's just not obvious all the time how to make it work. So you make a guess at how to make these alternatives, and if the situation is fairly complicated, it just may not be obvious how to pick these alternatives that we're going to surround it with. So for basic regression problems and density estimation problems, is fairly simple. They're all pretty straightforward. But when you get to complicated problems, it may not be obvious.
But the framework is still...
No, sometimes it doesn't work. So between Lecombe and Fano, I think I said you could probably solve 95% of all minimax problems. I think that's probably a fairly accurate statement. But it doesn't always work. There are other tools in the toolbox that you sometimes need to use. An example, actually, a recent example of this was a couple of years. Tony Kai and Harry Zhao proved some very minimax lower bounds about estimating large covariance matrices. And they had to create some new lower bounds. The standard techniques didn't work. So it can be very problem specific. But here, I'm going to show you now what's usually called the hypercube construction. So the following construction is a general way that often allows you to apply Fano's inequality. Okay, and it's exactly what I said. Let's suppose we're doing a regression problem. So how are we going to construct the n distributions? Well, I have to pick n regression functions. So I'll start with the 0 function. That's a good one. Then I'm going to chop it up into pieces. The size is to be determined. Then I'm going to start adding bumps. So the next one will look like this. Here's a bump. Maybe the next one will look like this. The size of the bump, we're trying to maximize the size while still keeping the KL distance small and making sure that we satisfy whatever smoothness constraint. Like if it's Lipschitz, it's going to look like a triangle. Here's another bump, and so on. So if I keep doing this, let's suppose I divide it up into m pieces. There's basically 2 to the m, or 2 to the m plus 1 functions in my set. So we can call any one of these distributions that results p sub omega, where omega is some sort of binary thing, each of these here is 0, 1. So this is just telling me if it's 0, don't add a bump there, and if it's a 1, add a bump there. Right? So now I can kind of parameterize all these functions by where I put a little bump. This is why it's called a hypercube. This now has the structure of a hypercube. And the distance between these functions is going to be some function of what? How many bits they differ in. If I have two functions here described by two different omegas, then the distance between the functions will be some function of what's called the Hamming distance, which is just how many bits they differ in. So I take this function, I take this hypercube, it creates a class of functions. This almost works, not quite. So now I could just compute, what do I have to compute? Just two numbers. The beta, which is the Kullback-Leibler distances between all the corresponding distributions, and the alpha, the distance between these functions. Unfortunately, if I do that, it's going to give me a bad lower bound. It won't work. And the problem is there's going to be many functions here that only differ in 1 bit. So they're going to be really close together. The alpha is going to be too small, it turns out. You see that? So if I have, this function has a bump, 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 missing a bump, and this one is bump, 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 bump. The L2 distance, say we're interested in L2 distance, it's going to be very small. Anything that differs in a Hamming distance of only 1, let's say, they're just too close together. So that raises the question. This hypercube construction starts out promising, but there's lots, when I look in these functions, there's lots of pairs of functions that are really close together, and that makes the alpha too small. Can I prune this? Can I pick out a subset of the hypercube which has almost the same number of functions, but which every pair is farther apart? And the answer is yes, obviously. This is a standard trick, and it's called the Varshimov-Gilbert construction. Okay? And basically, here's how it works. If you think of these things as, again, I don't draw this very well, but you think of them as being on a hypercube, like this is 0, 0, 0, 1, 1, 0, 1, 1. Can we reduce the hypercube a little bit so that we don't get things that are too close together? All you do is the following thing. You pick one, then you erase its neighbors. Then you pick another one, then you erase its neighbors. Okay? That's the construction. So that's lemma 12, which actually uses Hoeffding's inequality to prove this. But what this shows is, and this is important because it says that what makes this hypercube construction work, is that you can always take the hypercube and pull out some better suspects. And so what happens is that originally there was n. Originally we had what? 2 to the m of these. So originally there was m of these. Now there's n over 8 of them. However, the Hamming distance between any pair of them now is bigger than or equal to n over 8. Instead of being just 1 apart, they're always at least n over 8 bits apart. Okay, so just think of this as being a crowded set of distributions, and I've just thrown some out that are too close together. There's roughly the same number, but now no two are too close together. So that's a pretty cool trick. And it works in the sense that for most function estimation problems, this will give you the correct bound. So I'm just going to give you a sense for how this works now. I'm going to go back to the Holder class. So now I'm example 13, bottom of page 8. The steps are, we're going to construct the hypercube, we're going to prune it, and then we just compute alpha and beta and apply Fano's inequality. That's the recipe for computing these minimax lower bounds. So I'm going to now do the example. Any questions, though, before I jump into the example? All right, so this is example 13. It's the same example we just did, except I'm doing it more generally now. I'm letting it be the holder class where we have beta smooth derivatives. So it's the beta minus 1 derivative is Lipschitz. That's the class at the bottom there. So what you do is exactly what I said. And you have to think to yourself, how does he know how many little things to chop it up into? Well, it's trial and error, right? You try different settings for these things and you don't get the right answer and you have to kind of fool around with it a bit. So with some foresight, I can tell you that the right number of things to chop it up turns out to be this. So that's how many I'm going to take the unit interval and divide it into this many pieces. Okay? And then I write down a function for you, and it's just a kernel function. So we take, this is our blip function. Phi looks like this. It's some constant times h to the beta, where h is 1 over m, times a kernel thing centered at a particular point. What I'm doing is this is how I'm going to get something which is sufficiently smooth. I just take a little, we're used to using kernels, which are little smooth bumps. I'm going to take functions like this and place them here or place it here, wherever you want. That's the hypercube. And I do the integral for you there. The L2 distance between any two of these things turns out to be what does it turn out? Oh, there we go. So if I take two such functions, let's call one f sub omega and f sub v. I have the integral. The important thing here is that you can see it turns out to be, the L2 distance turns out to be the square root of the Hamming distance, like I said, times h. All I'm doing is I'm just integrating these. There's 0. The difference is 0 wherever they agree. And wherever they disagree, it's just the integral of this function. Okay? So this turns out to be of order h to the b. h is 1 over m, and we haven't picked m yet. That's kind of like our free parameter that we have to pick. All right. But we can also now compute the KL distance. It's the same calculation we did before, except this, there's this kind of little nasty function, but it's not so hard to compute. I wrote it down for you, and we want that to be, what do we want? Remember, we want that to be, well, first of all, it turns out to be something of order h to the 2 beta. But what do we need? We need that to be less than or equal to apply Fano's inequality, log n over 4n. But what's log n? This is where the number of things comes into it. N was like 2 to the m, except that we did the pruning. So it's 2 to the m over 8. That doesn't really affect anything. So this is equal to log 2 to the m over 8 over 4n, which is m over 32n. M is 1 over h, so let's write that as 1 over 32nh. But we need this inequality to hold. That tells us how to pick h, and hence m. You see, it's by setting this equal to the, it always comes down to getting that the Kullback-Leibniz distance satisfies this log n over n condition, tells us how to pick these tuning parameters in the thing. So that tells us, finally, that h has to be 1 over n to the 1 over 2 beta plus 1. And finally, we're done, because now we just have to say the minimax rate is, once I've chosen them to be this distance apart, according to Fano's inequality, I just take the L2 distance between, the smallest L2 distance between any pair, which we already computed. And so that turns out to be because remember, we showed that the distance between these were of order h to the beta. So if I put this h in here, I get the rate. And you get 1 over n to the 2 beta over 2 beta plus 1, which should look familiar. And again, if I'd done this in d dimensions, there'd be a lot more cubes, right? I would just put bumps over something like this, and all that happens when you keep track of everything is you get this. And we know that this bound is sharp because we have this, we know that we can get that upper bound using splines or using kernels and things like that. Now I realize I went through this really fast. And some of these calculations, when you write them out carefully, you know, they're kind of tedious. But this basic strategy is the most common way of proving these non-parametric minimax bounds. I'm going to summarize it for you again. If all you care about is something like at a point, you can just pick two distributions and do Lacombe. If you're doing something which is involving integrating an error, you'll find out that Lacombe, it'll still give you the rate, by the way, but it'll probably be off a little bit. It may not be sharp in all cases. But typically people will use Fano's inequality, and all we're really doing then is taking a base function, making lots of little blips around it. That's our finite set of distributions. The next step is to prune it using the Varlamov-Gilbert technique. And now the only thing left to do is compute the KL distance between each pair and make sure that's log n over n. That will set for you any free parameters that you had lying around. And now you're done. Now you just take each pair of functions and you say how far apart are they in the metric I'm using, and that gives you the minimax rate. Now, as I've said, there's a lot of exceptions, though. I mean, not everything's that simple, but a lot of problems. That's basically what's going on. So for the remainder of the class, I don't want to do more calculations. You've had enough calculations. I just want to highlight some places where this has been used in interesting ways. Let me pause, though, because again, I know I went through a lot of stuff quickly, so I want to see if you have any questions about anything there.
So we can only use this method when we care about a certain point?
No, this is for the L2 distance. Actually, what I just did works for any metric. So the calculation here, when I said this was true, I did that under the L2 distance. You just put in whatever distance you want. Yeah, if you're interested in the whole function, use Fano. If you're interested in one point, use Lacombe. That's a kind of good rule of thumb.
So for the upper bound, I just pick the one I have the most facing in, that will give me the minimax rate.
Well, you hope. So the upper bound, if you know I have an estimator and I know it's upper bound and it matches that, you're done, right? And that's often what happens. In fact, it often goes the other way around. You have an estimator for whatever reason. Then you think, I wonder, is this estimator any good? Well, they have to ask yourself over what class of distribution. So you think, maybe over this class of distributions. Then you say, I need to find the lower bound. And if that lower bound matches the rate of the estimator you have, you've now shown, not only do you have an estimator, but it's optimal over this class. But sometimes they're going to be different. And then you don't know, you're going to have to do some work, right? Is the upper bound loose or is the lower bound loose? One of the two must be loose, and it's sometimes not clear which one. Yeah, so I don't want to make it seem easier than it is, because in some problems this can be quite difficult.
So these functions that we are using, the base function and the bumps, do we need to ensure that they are density functions, or can they be like arbitrary functions?
Well, we are dealing with distributions. So these bumps are on the regression function, the way I was talking about it. But to use Fano's inequality or Lecombe's inequality, you still have to somehow end up with distributions. So the way we did it here, remember, is there's actually an underlying distribution. And I specified a distribution for x. And I specified that the distribution for y given x was normal, whose mean was the regression function. So you've got to take the class of functions you're dealing with, regression functions, and somehow turn them into probability distributions. Yeah, these lemmas are about probability distributions. So even though we're dealing with regression functions, somehow we have to transform ourselves back into the world of probability distributions.
So are there examples where the lower bound is known and I guess agreed upon, but there's no there's no estimator that can achieve it yet?
Depends what you mean by estimator. There are definitely examples where there's no computable estimator known to achieve certain lower bounds.
So was that sparse PCA?
Yes, sparse PCA is the perfect example. I'll tell you another example I happen to be familiar with. Is I wrote a paper with some colleagues about estimating manifolds. And the upper bound matches the lower bound, but the upper bound is uncomputable. And to this day, nobody has come up with a computable estimator for that problem.
Sparse regression, we don't know. The subset selection estimator achieves the minimax bound over all X matrices. We don't know. There is that recent paper. We don't know whether there's a polynomial.
Yeah, who was that by again?
Wainwright and Jordan.
Oh yeah, that's right. Mike Jordan and Martin Wainwright have a recent paper about subset regression. Yeah, no, there's lots of cases where there's gaps. Okay, so just to, oh yeah.
So for picking this kind of P, it seems very arbitrary. Are there any kind of typical choices that we can use except this one?
The most common examples are the one I just did. You take some simple function and you add little perturbations to it. That's almost always how it's done.
Even in high dimensions?
Even in high dimensions. That's typically how it's done. I'm sure if I thought about it longer, I'd find some exceptions where they're different than that. But, well, actually, I am going to tell you one in a minute that's a little bit different. But 99% of the time, that's because no one knows what else to do. And it usually works. All right, now I want to mention just a few sort of anecdotes that are just sort of things you can read. You can read the details if you're interested. I know some of you find this fascinating, so you'll want to read through the rest of the notes carefully. Some of you couldn't care less about Minimax theory, so if you don't want to read the rest, that's okay. But let me just give you a kind of preview of what's in here. First of all, in section 6.1, I explained the actual minimax theory for maximum likelihood estimation. It is surprisingly complicated. You might think parametric inference would be easier, but you might take a look at theorem 14, which is the Hayek-Lecombe theorem, which you're going to spend a while parsing that equation, but it's telling you that maximum likelihood is minimax asymptotically. But it's surprisingly difficult to make that precise. But at an intuitive level, you can think that in well-behaved parametric families, and that means fixed dimension, nothing funny happening, the MLE is at least asymptotically minimax. I also put in another worked example, 6.2, if you want to see another example, where I did density estimation and I changed the metric, so you can see how the calculations are done. And we get the usual rate. 6.3 goes over classification. And in particular, the purpose here was to try to explain something that everybody knows is true. We all know, in a certain sense, that classification is easier than regression. We proved that in 705 because we showed that the classification risk is less than or equal to the regression risk. But we also know it in a kind of a practical level, because if I try to do regression in like dimension 5,000, forget it. You're not going to get good answers. But we do classification in high dimensions all the time. Think about images. Those are super high dimensional objects, and we can do it really well. Think about your email. You're counting how many different words there are, and how many times certain words appear on your email. That's a super high dimensional object, yet your spam filter works pretty good. And so this Minimax theory that I outlined here is what I think of as the best explanation. It's due to Sasha Sibikov and a few others, which just to get to the heart of the matter, you can read through the whole thing if you want, but we all kind of know intuitively why this is true, but this makes it precise, which is, remember this picture that we know the optimal classifier classifies 1 if m of x, the regression function, is bigger than a half, right? So if this is the regression function, this is a half, the regression function might be super complicated, and I might have a horrible, horrible estimator. Maybe my estimator looks like this. But as long as I kind of get the basic story right around the decision boundary, it won't matter, right? It doesn't matter if I estimated it poorly here. So in some sense, it's obvious. But how do you make that mathematically precise? And the way Sibikov did it is he introduced this thing called the low noise assumption, or sometimes called the Sibikov assumption. Sometimes it's called now the margin assumption, which is simply that right at the decision boundary, you want to make sure that there's not the probability, I'll write it out this way, the probability that the regression function minus a half, so that's the decision boundary, less than t, is less than or equal to some constant times t to the alpha. So what is that saying? This can happen in two different ways. Suppose alpha is large. You want alpha to be large. What that's saying is the probability right near here is small. But actually that can happen in two different ways. It could be that this is very sharp. That means then when you're in here, this exponent's going to be big. Or it could just mean that the marginal probability doesn't put too much probability there. Or it could be some combination of those factors. Then it turns out that the minimax rate of convergence has an unusual looking form. It's different than anything we've seen in the class so far. And it looks like this. Okay. What is this stuff? Alpha, we already saw what alpha is. Rho is some sort of, think about this as kind of a smoothness assumption, not on the regression function, but on the decision boundary. But here's the interesting thing. When alpha is large, if you think about letting alpha go to infinity, so I think we're in a low noise situation, this becomes like almost 1 over n, independently of dimension. Well, this is showing you, in some sense, an explanation of why we can classify very accurately in high dimensions. It's not the only possible explanation, but this is an explanation of why we can classify well in high dimensions. This is what I think of as sort of why minimax theory is useful, is it forces you to think about, we're doing well in this situation, let's try to explain why. It's not the other way around, right? It wasn't that someone said, I'm going to put down these conditions and get this right and now declare that classification is easy, right? That would be useless. It's the other way around. It's that we're noticing that classification somehow works well in high dimensions, even though the standard theory predicted otherwise. So obviously, the standard theory is not including assumptions that are describing the real world. What's describing the real world often is simply that we're not, that either we have a pretty sharp decision boundary or we're not putting there's not a lot of probability into the decision boundary or some combination of those things. And the resulting minimax bound shows you that that's the case. And then there was a follow-up paper by, I'm going to blank on their names, some Hungarian guys, which showed that all the basic classifiers, like just doing kernel regression and using that as a plug-in classifier, automatically adapt. They automatically achieve the fast rate of convergence if the low noise assumption holds. So that's also interesting, because what that says is if the low noise assumption holds, you don't need to do anything special. Your standard classifier will just automatically have a lower classification, better classification error. So there really is something to be learned by thinking about things this way and by working out the rates and so on. I still, there's other explanations about what's going on, but I do think this is probably the one that I find the most convincing. But let's talk about another one. There's a few other surprising ones. So we may have a lecture on active learning in a couple of weeks, in which case you'll see that if you get active learning means you get to say, I want to see the y that goes with this x. I want to see the y that goes with this x in a sequential way, and you'll see that that changes the minimax rate. Being able to probe things sequentially allows you to reduce the minimax rate. In some problems. In other problems, it doesn't change the minimax rate. So it tells you when does active learning work. So that'll be another example we'll see possibly in a couple of weeks. OK, here's one of my favorite examples, though. And this is a very much underappreciated example. This is on page 16. And this is the problem of what's called measurement error. And it just shows you how surprising things can happen. So let's start with what we consider to be an easy problem. I'm sampling from x1, xn distribution, and it has a density p. Let's say I'm in one dimension. OK, and so we know the minimax rate depends on the smoothness. Let's say 2 beta over 2 beta plus 1. When we take beta equals to 2, the most common case, that's 1 over n to the 4/5. No problem, right? That's an easy problem. Now comes the surprise. And I think this is something that I would say most statisticians know about, but seems to be not known in machine learning, which is suppose I can't observe the x's directly. Suppose instead of observing x, I observe x plus a little bit of error. So I observe y is equal to xi plus a little bit of error. This could be very small. And so what you're observing, so if I draw this like a graphical model, and these are hidden. And epsilon is going to be, let's say, normal. This is really something that actually happens quite often, and people tend to ignore it. What happens to this 1 over n to the 4/5? Well, it's shocking. It becomes, the minimax rate becomes 1 over log n, which is, for all practical purposes, constant. It doesn't even go to 0. I mean, it does, but it's so slow, it's hopeless. Yeah?
Should that depend on the variance of the...
Doesn't depend on the variance. Well, it does depend on the variance. There's a constant here which depends on the variance, yeah. But I'm thinking of the variance as some fixed number. You're right. If the variance, of course, went to 0, it would be back to the, yeah. But what it depends on even more, this is what's surprising, is I said epsilon is normal. That's the worst case. It turns out in this problem, you always think of right as the Gaussian as the best case. Everything good that happens with the normal. This is the big counterexample to that. The worst rates occur when the error is normal. It's a very surprising fact. And this is really important because there really are a lot of things where there's measurement error, and people tend to kind of brush that aside. But this is a dramatic difference, right? I find this to be one of the most surprising things, that comes out of this stuff. And the proof, here's where the proof kind of differs from the standard Fano thing. If you try to do this, work out the rates, by putting little wiggles around the density, you're going to be in for a surprise. You're going to get back the usual rates. That doesn't work. You're going to end up with a lower bound that doesn't match the upper bound. The upper bound, by the way, uses a type of kernel density estimator, but with a specially designed kernel to account for the measurement error. But the upper bound, it's easy to see, converges at 1 over log n. So you find out, if you try to use the standard Fano thing, here's the situation you end up with. You're trying to get this rate, and you have an estimator. Imagine you're the first guy who did this. You have this estimator. You create this estimator, and you go, oh, my God. When I do the bias and variance, look how slow this is. Let me work out the lower bound. You add some wiggles to the density. You get back 1 over n to the 4/5. Something's wrong. Something isn't tight, right? It's the lower bound. The trick is this. You have to go to the Fourier domain. You take the Fourier transform of the density, and you add wiggles in that domain. It turns out that's just the right thing to do. So there's a case where it's not obvious at first how to do it. But if you do the kind of Lecombe thing in the Fourier domain, it works. And you get 1 over log n. And so we know that's optimal. That's the best you can do. It's not that the estimator is bad. That's important, right? It's not that the estimator is bad. It's that that's the best you can do. So that one is a kind of interesting and surprising situation. The same thing happens in regression. The same rate holds in regression. I did density estimation, but I want to be clear about where the errors are. So when you're doing regression, we always assume you've got these x's and y's. You could be doing linear regression, non-parametric regression. Let's even assume the linear model is true. So here's our, it doesn't have to be linear. Let's even do non-parametric. Yeah, let's say non-parametric. But a fundamental assumption that you've probably always made through every course you've ever taken is that you can observe the x's directly. But there's lots of cases where you can't. My favorite example is secondhand smoke. Suppose this is secondhand smoke and this is disease. You can't measure how much secondhand smoke somebody's had. The way they measure secondhand smoke is they interview people and ask them, how much smoke do you think you've inhaled over your lifetime? They don't ask it that way, but they say, like, have you worked in a bar, da, 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 and it's estimated. At best, you're getting a noisy version of this, right? So actually, when you have regression, when the x's aren't measured precisely, this is called errors and variables, you actually have a pair of equations. What you're observing is w, which is, say, at best, epsilon plus, say, another error. Again, this is something that gets swept under the carpet a lot, but this is often what's really going on, is you have a regression of y on x, but you don't get to observe x. So x is hidden here. The graph will look like this then, is that x arrow y and w arrow x. I'm interested in this relationship, but I don't see x. So even in the linear case, suppose I just had a linear regression. If you do linear regression of y onto w, even then you get an inconsistent estimator. But it turns out that's an easy one to fix. There's some simple tricks to fix it in the linear case, okay? Which are kind of cool, but I'm not going to, that's a kind of diversion. How about in the non-parametric case? The non-parametric case, unfortunately, it's the same story, which is if you really want to estimate the function m, you're going to get back the 1 over log n rate. Now, let me clarify, though. If all you care about is prediction and not estimating m, you could just ask yourself, as a prediction problem, how well can I predict y from w? You don't need to worry about estimating m. And you might still be able to predict well. You may be able to predict well. You may not be able to predict well. It depends on the situation. But if you actually want to understand this relationship between y and x, you're in big trouble, because this is another example of these slow minimax rate. And without minimax theory, people would still be scratching their heads trying to come up with better estimators. That's the thing, right? You come up with an estimator, it's got this slow rate of convergence. You think, oh, I just better try harder and come up with a better estimator. But then you think, oh, luckily, my professor taught me Fano's inequality. I know how to compute the lower bound, and I can see that's as good as you can do, and so it saves you 5 years of your life. Okay. let's see if there's anything else that I can do quickly. Okay, the last thing, again, I'm just covering kind of a smattering of extra topics here. And this is just kind of a cool thing. This is page 20. It's also due to Lacombe. Because Lacombe figured out that in many cases, the whole problem of finding the minimax rate can often be reduced to solving a single equation, the Lacombe equation. This is it. All right, let me explain what this is. It's a nice equation. And what's happening here is the right-hand side is going like this. The left-hand side is going like this, it turns out, and we're trying to find kind of this equality point. What is this? Remember I mentioned the other day something called covering numbers. N of epsilon was the number of balls of size epsilon to cover the space, and h is the log of that, sometimes called the metric entropy. So there's a large class of problems where if you can just take the space of functions, compute this metric entropy, and set it equal to n epsilon squared and solve it, often that will give you the minimax rate. That's called the Lacombe equation. It's not always true, but I did outline here actually a proof of this for the case of when the typical case this works in is if you're trying to estimate a density function non-parametrically, and you have some class of densities. And if you compute this covering number, so the VC dimension here, if you can define that for functions as well, and it's typically infinite. So that VC theory doesn't help us, but we can use this metric entropy, solve this equation, and that gives you the minimax rate without having to go through all that pain. And that would be really useful if we knew what the metric entropy is, or the covering number was for different spaces, and you do, because I put them on page 24. So on page 24, I listed some common spaces. Did we talk about Sobolev spaces in this class? We did, yes. Sobolev space is very similar to Holder space. So what I've done is I've made a little table for you. Like here's the Sobolev space. There's its metric entropy. And then if you just solve that equation, you get that rate. Lipschitz monotone functions have entropy 1 over epsilon. You solve it, n to the 1/3. So if I'm telling you estimate a density function, and I'm telling you it's an increasing function, you now know that 1 over n to the 1/3 is the minimax rate, just by solving that equation. Bessoff spaces, they're more complicated spaces. Ryan talked briefly about wavelets. They're designed to work well over this larger class of functions called Bessoff spaces. There's the rates for that. An interesting one is neural nets. I tried to find, so I wrote a typical neural net here where it's like a sum of these, say, sigmoidal functions or step function or something like that. And I cannot find a bound on the a precise answer for the metric entropy. Maybe it's been discovered, but the best I was able to find are upper and lower bounds, which I've given in equation 51 there. It's possible I just didn't find the most recent reference, but that was the best I was able to do. Is that there's an example where, as far as I know, the exact answer isn't known, although this might be a few years out of date. All right, so let me summarize now what we've learned in 1 minute. Is I hope I've given you an appreciation for how you might go about finding a minimax bound, should you want to do so. More importantly, I hope I got across the idea that it's a useful thing to do when you want to understand how difficult a problem is. And in particular, one thing you have to be wary of is people make up classifiers, estimators like that, right? Here's a classifier. I just invented a classifier. Everybody and their uncles made up a classifier. Is it any good? That's one question you should always ask yourself. When is this classifier going to work well? So you should always get in the habit of saying, oh, my classifier or my estimator is going to work well under the following assumptions for the following distributions. Nothing works well universally. Everything requires assumptions. So understanding when your classifier or your estimator is going to work well is really important. Once you've done that, you can now ask the question, is there anything better? How do I know that given those assumptions, I can't do better than that? And that's what minimax theory is useful for, is that if your classifier or estimator achieves the minimax bound, you've got the best. If not, you know you can do better. So that's kind of what that stuff's all about. All right, so any questions? All right, the next couple weeks, then we're going to be doing special topics. Some of them you requested. Some of them you didn't. But hopefully they'll be interesting anyway. Remember the homework, 1 week extension, if you need it. It might be better in your mind to imagine you don't have the extension and try to get it done anyway, but that's just some advice.